Hello everyone, I am Dr. Gitumoni Sharma, Associate Professor, Department of Mathematics, USTM. I am going to take a class on special theory of relativity. Today's my topic is time dilation, a consequence of Lorentz transformation. Let me talk first about keywords of my lecture. Lorentz transformation, consequences of Lorentz transformation and time dilation. So, Lorentz transformation we discussed in our previous classes. It is a mathematical method of testing. It is a relation between two coordinates x, y, z, t and x dash, y dash, z dash, t dash with respect to s prime and s dash prime. And Lorentz transformations equations are x dash is equal to x minus v t divided by root over 1 minus v square c square, y dash equal y, z dash equal z and t dash is equal to t minus vx by c square. So, these are known as Lorentz transformation equation. Now, time dilation is the difference in elapsed time as measured by two clocks either due to a relative velocity between them, special relativity, or due to a difference in gravitational potential between their location. It is included in general relativity. When unspecified, time dilation usually refers to the effect due to velocity. So, first of all we should know that what is the time dilation. It is the observation of two observer which are in relative motion, and when two observer in relative motion and they are going to measure time difference, then their time time measurement is different. So, this is the time dilation, and it is the first part in special relativity and second part in general relativity, and which not specified, then this is known as the effect due to a velocity. One of the most fascinating prediction of special relativity is that of time dilation. What is time dilation? If time is measured by two different observers who are in relative motion with respect to each other, their measurement are going to be different. Now, in classical and Newtonian physics, we think of time is absolute or very much independent of the observer in reference frame. So, in classical physics, we read in our previous classes that velocity of light is constant. So, we discuss in details in our previous classes here, but in relativity little bit different. In relativity, time is very much dependent on which the reference frame is situated. We can prove that by a simple experiment. So, in classical physics, speed of light is independent, and in relativity speed of light is dependent. Two relative observer observe the speed of light differently. So, this is the main important thing, and one of the most fascinating prediction is of special relativity or consequence is the time dilation. So, about time dilation we are going to discuss in details. The two observer here, one is rest observer and another is moving observer, and if the two observer going to measure the time difference with respect to the frame of reference, then their measurement are going to be different. We know that there are four Maxwell's laws of electromagnetism. These are not invariant under Galilean transformation, as Maxwell gives the result that light is an electromagnetic phenomenon. So, Einstein accepted that a new mathematical method of testing would have to be derived so that Maxwell's laws also invariant in both frame of reference. So, here given that why Lorentz transformation is important, for what purpose Lorentz transformation has to be derived. So, already you know that there are four electromagnetic law. These are the Gauss law in electricity, Gauss law in magnetism, Faraday's law of electromagnetic induction and Maxwell's law of electromagnetic induction. As Galilean not proved that Maxwell's electromagnetic theories are invariant, so another mathematical method of testing known as Lorentz transformation has to be derived. So, this is given that light is an electromagnetic phenomenon and it has velocity 3 into 10 to the power 8 meter per second. Galilean transformations are approximation of Lorentz transformation for speeds very lower than the speed of light. Lorentz transformations are valid for any speed, whereas Galilean transformations are not. So, these are the basic concept for before we study the time dilation. We need to know that difference between Galilean transformation and Lorentz transformation. Galileo formulated the principle of relativity in order to show that one cannot determine whether the earth revolves about the sun or the sun revolves about the earth. The principle of relativity states that there is no physical way to differentiate between a body moving at a constant speed and a immobile body. So, these are the basic concept between Galilean transformation and Lorentz transformation, and why Lorentz transformation is derived, that is one of the important point for studying time dilation. Lorentz transformation are required to describe high speed phenomena approaching the speed of light. Lorentz transformation formally express the relativity concept that space and time are not absolute, that length, time and mass depend on the relative motion of the observer, and that the speed of light in a vacuum is constant and independent. So, using Lorentz transformation equation, we show that space and time working together, because in Lorentz transformation equation we get x dash is equal to x minus Vt divided by root over 1 minus v square c square. Other two x's are parallel, y and z, and t time component we get, it is t dash is equal to t minus vx by c square whole divided by root over 1 minus v square c square. So, space and time, x means the x represent the space coordinate and t represent the time coordinate. So, Lorentz transformation shows that how space and time working together, and speed of light is constant in vacuum and it is independent. Now, we are going to discuss the thought experiment, which is very helpful to understand the time dilation, which is a consequence of Lorentz transformation. Let us imagine there is a train and the train is moving in a certain direction with a constant velocity v. Inside the train there is a particular setup. In the ceiling there is a bulb which can emit light. So, first of all, what we do, we consider a train, and train is moving in a certain direction with a constant velocity v, and there is a certain setup. So, first consider a bulb which can emit light, and light flow downwards and reach the floor. There is a detector on the floor and detect the light. So, it is the picture. See, picture A shows that light emitted bulb emitted light, and light reaches the floor straightly. There is a detector on the floor and detect the light. Let us suppose we switch on the light for an instant and light comes out. Light travels a particular distance and reaches the floor and detect by the detector. So, see in picture A, the light reaches the floor straightly and it is detected by the detector which is on the floor. Let us suppose we switch on, light travels a particular distance and reaches the floor and detect by the detector. Let us define two physical events. Physical events 1 happen when light has been emitted by the bulb at point A, and physical events 2 happens when light reaches the point B and is detected by detector. I want to measure the time period between two events. So, there are two events, one is the at point A, that is the bulb, and another is the at point B. So, physical event 1 happens at point A and physical events 2 happens at point B. Physical events 1 is the when light reaches the point, and B is the detected by the detector. So, two event consider. Now, I want to measure the time period between the event A and B. Here both two pictures given, A and B. So, first picture say that there are one inside observer, and second picture shows that one outside observer observe the whole situation. basically I want to measure the time period which take time period from the point A to the point B. There is a observer inside the train. For an observer inside the train, the entire setup of the bulb and the detector is at rest. So, this is the picture A. This is the picture A for the inside observer. He says that whole the entire setup inside the train is at rest position. Bulb and detector, they are at rest position. So, for him time period is distance covered by the light divided by speed. So, in that case time period denoted by delta T naught, and it is equal to h by c. H is the distance, h is the distance between bulb and the detector, and c is the speed of light. So, it is the time period detected by the inside observer, which suppose the height of the train is h and speed of light is c. Now, if you remember the second postulate of special relativity, it says that speed of light is always constant. It does not matter from which inertial frame of reference is measuring it. So, we always use the speed of light is constant, it is c. So, in special relativity we discussed two postulates, one is the principle of relativity and another is the universal constancy of speed of light. Principle of relativity says that all physics law must be same in all inertial frame, and speed of light is second postulate said that speed of light is universal constant. Now, there is a question, inertial frame means what? Inertial frame means where velocity v 0 or velocity constant. So, that frame is known as inertial frame. Now, if we make the same measurement but by the different observer perspective, let us suppose we have the similar situation. The observer, instead of the inside the train is now on instead of the inside, the train is now on the platform. The train is moving in a certain velocity, but observer is looking at the same physical event but from the platform. So, now in this second condition we consider the observer is platform, that is the outside observer we consider, and similar situation observed by the observer, but he is not inside the train, he is outside the train, he is on the platform. So, for this particular observer, light travel in a different path. So, what the light is emitted by the bulb at the train is a particular location. So, outside observer observed that light is not a straight line, light is light following a different path, and so that he said that it is different because the train is moving by the time light ray reaches the detector, train would have traveled and travels in a particular direction. So, in that case, second situation, when observer is outside, then he said that train is also moving and at the same time bulb is also moving, where bulb is situated inside the train and bulb emits light. So, in both are the moving in a forward direction, train and the light ray. So, he said that light not a straight line, light not reaches the straight way, it reaches the floor in a different way. So, the effective path which is travelled by the light ray as it goes from the bulb to the floor is not vertical downwards direction, but rather along the hypotenuse of the right angle triangle, where this is point A. This is the point B, and this is B dash. So, this is the picture A, B and B dash. This is a right angle triangle. When the light bulb emits light and it travels in a bending way when train is moving in second situation, and this situation observed by the outside observer which is on the railway platform. So, he said that light in along this hypotenuse, and this angle is a right angle triangle. So, the effective path which is travelled by the light ray as it goes from the bulb to the floor is not vertical downwards direction, but rather along the hypotenuse of the right angle triangle, where the point is A and second point B, and let's the third point is B dash, which is where the detector would be after the travel certain point in time. Let's suppose the time is for the light ray to travel from ceiling to floor is delta t. In that case, the distance between the train is, it is the time period, see the picture, time period is delta t from between the point A and B, and A is the initial point, A is the point where bulb is located, and B dash is the point where light reaches the floor in a hypotenuse direction of the right angle triangle A B B dash. So, delta t, in that case the distance which the train has travel in that period of time d is equal to v into delta t. So, distance is equal to velocity into time period. So, if the distance is velocity multiplied by the time period, the path length would therefore be root over h square plus v square delta t square, because it is a right angle triangle. So, in a right angle triangle we know that hypotenuse square is equal to base square plus perpendicular square. Therefore, we get root over h square plus v square delta t square. So, it is quite simple. Time period is delta t is equal to distance by speed of light. Therefore, distance is root over h square plus v square delta t square divided by speed of light, and simplifying we get that delta t square is equal to h square by c square plus v square delta t square by c square. After simplification we get result. Now, I have already obtained that h by c is nothing but the time period measured by an observer in the train. So, substituting this value h by c, we get that it is delta t naught. So, in our previous slide you can see here delta t naught is equal to h by c. Putting this value we get delta t square, and both sides squaring both side we get delta t square is equal to h square by c square plus v square delta t square divided by c square, and simplifying we get delta t common, delta t square common into 1 minus v square by c square is equal to delta t naught square, and simplifying taking square root we get delta t is equal to delta t naught divided by root over 1 minus v square by c square. Now, one important term is here 1 by root over 1 minus v square by c square. It is known as Lorentz factor, and it is symbolized by, denoted by gamma. So, when root over, and another important point here, root over 1 minus v square by c square always less than 1. Therefore, we get delta t dash greater than delta t, delta t greater than delta t naught, and delta t is the time period when train is moving, and delta t naught is the time period when train is at rest position. Therefore, we get delta t greater than delta t naught. As you can see here, delta t is the time period measured in between the two events in which light leave the light and reaches the detector for the perspective observer on the platform, and delta t naught is the time period between exactly same two events, but from the perspective of the observer which is inside the train. So, they are not same because of the particular factor. So, this is the main factor 1 by root over 1 minus v square by c square known as Lorentz factor. So, the delta t and delta t naught not same. Delta t is the time period when train is moving in a certain direction with a particular velocity, and delta t naught is the time period between two events, bulb and the detector, when train is the rest position. Now, we are going to we say that delta t not equal to delta t naught. And since the phi here not exactly going to be 0, this term here some kind of value, and therefore, these two term is not going to be the same. This is the time dilation expression for time dilation, but we do not really express experience time dilation in normal day to day life because a velocity in which bodies move in not necessarily that, but we don't really experience time dilation in normal day to day life because a velocity in which bodies move is not necessarily that high that the particular term create can effect. Let us look at the few example. Now some example we are going to discuss where the Lorentz consequences time dilation is applied. Normal day to day life time dilation is not applied because here V not exactly going to be 0 this term. So now we are going to discuss some example. In the first case, I have taken the example of very first moving jet fighter plane which has speed 3000 km per hour, which is a very fast moving fighter plane. So first example we take one fighter plane and it has velocity 3000 km per hour, which is a very fast moving fighter plane. If I put this value in the expression, we obtain so that time period difference between fighter plane pilot which is flying and somebody of the on the ground comes out to be 0.00000385%, which is a very small difference. But if I make the same calculation for, let us suppose, for other particle which is moving with half velocity of light, in that case difference to be 15%. And if I take the time dilation for same particle which is moving 90% of speed of light, time dilation comes out to be 129.46%. So as you can see, in our normal day to day life, when we encounter velocity which is a much less compared to speed of light, time dilation effect are non-significant at all. But when we talk about velocities closer to the speed of light, in those cases time dilation effect becomes quite significant. So time dilation is only applied when the speed of light, when the velocity of a moving frame is very high and it is closer to the speed of light, then the time dilation is time dilation and other consequences are applied on and that situations happen, and in our normal day to day life these are not happen. So this is the velocity of the fighter plane 3000 km per hour. Then we find the ratio v square by c square, and after calculation we get 0.077098 into 10 to the power minus 10, and then the time period, time difference, time measurement is delta t is equal to 1 by root over 1 minus 0.077098 into 10 to the power minus 10. After calculation it will be 0.0000000385%. So it is very small difference. In picture 3 we shows that when velocity 0.9 into c, then we get the time difference delta t is equal to 129.46%. When velocity half of the speed of light, then we get delta t is equal to 15.47%. Now we are going to discuss about the brief history of the time dilation, why time dilation happens, and Lorentz transformation equation. So all these things explained in this slide. After compensating for varying signals delay due to the sensing distance between an observer and a moving clock, that is Doppler effect, the observer will measure the moving clock as ticking slower than a clock that is at rest in the observer own reference frame. In addition, a clock that is close to a massive body and which therefore is at lower gravitational potential will record less elapsed time than a clock situated further from the said massive body and which is at a higher gravitational potential. So these are some explanation about the history of time dilation. These predictions of the theory of relativity have been repeatedly confirmed by experiment and they are of practical concern. For instance, in the operation of satellite navigation systems such as GPS and Galileo. So, in the GPS, Galileo or any other application, there are so many things happens like time dilation and length contraction, relativity of simultaneity, all those are consequences of Lorentz transformation. This indicates that for an observer in an inertial frame of reference, a clock that is moving relative to them will be measured to tick slower than a clock that is at rest in their frame of reference. This case is sometimes called special relativistic time dilation. The faster the relative velocity, the greater the time dilation between one another, with time slowing to a stop as one approaches the speed of light. So, relativistic time dilation is what that definition is given. Theoretically, time dilation would make it possible for passengers in a fast moving vehicle to advance further into the future in a short period of their own time. For sufficiently high speeds, the effect is dramatic. For example, 1 year of travel might correspond to 10 years on earth. Indeed, a constant one, the acceleration would permit humans to travel through the entire known universe is one human lifetime. With current technology severely limiting the velocity of space travel, however, the differences experienced in practice are minuscule. After 6 months on the International Space Station, orbiting Earth at a speed of about 7,700 meter per second, an astronaut would have aged about 0.005 seconds less than those on Earth. The cosmonauts time dilation can be inferred from the observed constancy of the speed of light in all reference frames detected by the second postulate of special relativity. This constancy of the speed of light means that, counter to intuition, the speeds of material object and light are not additive. It is not possible to make the speed of light appear greater by moving towards or away from the light source. Consider then a simple vertical clock consisting of two mirrors A and B, between which a light pulse is bouncing. The separation of the mirrors is L and the clock ticks once each time the light pulse hits mirror A. So, this is about the two mirrors A and B, and between the two mirror a light pulse light beam here travels, and then we get the time dilation. In that case also we discuss time dilation. In the frame in which the clock is at rest, the light pulse traces out a path of length twice L, then the period of the clock is twice L divided by the speed of light. Given a certain frame of reference and the stationary observer described earlier, if a second observer accompanied the moving clock, each of the observers would perceive the other's clock as ticking at a slower rate than their own local clock, due to them both perceiving the other to be the one that is in motion relative to their own stationary frame of reference. So, in case of clock, same situation happen, time dilation happen. Common sense would dictate that if the passage of time has slowed for a moving object, said object would observe the external world's time to be correspondingly speed up. Continuatively, special relativity predicts the opposite when two observers are in motion relative to each other. Each will measure the other's clock slowing down in concordance with them being in motion relative to the observer frame of reference. While this seems self-contradictory, a similar oddity occurs in everyday life. If two person A and B observe each other from a distance, B will appear small to A, but at the same time A will appear small to B. Being familiar with the effects of perspective, there is no contradiction or paradox in this situation. So, this situation is known as paradox. Two observer here, one is A, another is B. A has one clock and B one clock. B has one clock, and they if A rest and B moving, and then he said that A clock is faster than the clock B. So, it is known as clock paradox. Now, we are going to discuss about the time dilation in case of a rod. So, this is the picture S frame and S dash frame, and here one rod is considered between 2 point x1 and x2, and A is the position of the rod, and it is inside observer in S frame and outside observer which is in moving with a S dash frame. Suppose two events occur at the same place x0 at times t1 and t2 in S frame. The corresponding time according to S dash are t1 dash and t2 dash. So, according to S dash frame, each time when it observed the situation, observed the rod, so according to S dash frame, time is t1 dash and t2 dash, and events are at the same place, A place x naught given, and it is between 2 points x1 and x2. Then from Lorentz transformation equation, delta t dash is equal to t2 dash minus t1 dash. Delta t dash is the time measurement with respect to the S dash frame. So, delta t dash is equal to final time period minus initial time period, t2 dash minus t1 dash. So, in applying the Lorentz transformation equation, t is equal to t dash is equal to t minus vx by c square whole divided by root over 1 minus v square by c square. We get that after simplification we get t2 minus t1 minus v by c square into x naught minus x naught, because here the same place consider. So, x2 minus x1, instead of x1 minus x2 we write x naught minus x naught, because same place consider, whole divided by root over 1 minus v square c square. So, second term will be 0, only we get delta t divided by root over 1 minus v square by c square. After simplifying we get delta t dash into root over 1 minus v square by c square is equal to delta t. So, given equation 1, since root over 1 minus v square by c square less than 1, so delta t dash greater than delta t. See here, this term, the root over 1 minus v square c square less than 1, so we get delta t dash greater than delta t. So, delta t dash is the time period with respect to S dash frame, and delta t time period with respect to S frame. Thus, the time interval delta t dash measured from S dash is larger than the time interval delta t measured in S. Now, we are going to discuss about some experience given by Einstein. One evening in the spring of 1905, Albert Einstein, then a patent clerk in Bern, after trudging through his day's work, decided to board a tram car on his way home. So, Einstein explained this experiment by his own experience. Einstein would often wear up his work as soon as possible to contemplate the truths of the universe in his free time. It was one of his thought experiment he devised on that tram car that revolutionized modern physics forever. While receding away from the Ziegler clock tower, Einstein imagined that what would happen if the tram car were receding at the speed of light. he realized that if he were to travel at 186,000 miles per second, the clock hands would appear to completely freeze. At the same time, Einstein knew that back at the clock tower, the hands would tick along at their normal place. So, he just observed the situation when the tramcar move at a speed of light, with the speed of light, then what situation happen? When the tramcar is at rest position, then what situation will be happen? For Einstein, time had slowed down. This thought blew his mind. Einstein concluded that the faster you move through space, the slower you move through time. So, he gave one conclusion that when you move through space, then your time slowed down. Einstein's work was heavily influenced by two of the most iconic physicists of all time. First, there were the laws of motion discovered by the Newton, and the second were the laws of electromagnetism laid down by James Clerk Maxwell. Newton's laws insisted that velocities are never absolute but always relative, so that their magnitude must be appended by the phrase with respect to. For instance, a train travels at 40 km per hour with respect to someone at rest. However, it only travels 20 km per hour with respect to a train traveling 20 km per hour in the same direction. Or it travels 60 km per hour with respect to another train traveling in the opposite direction at 20 km per hour. So, three train he considered, one is moving with velocity 20 km per hour, one is with respect to one observer, he said that it is moving 60 km per hour, and which is in opposite direction, he says that it is 40 km per hour. So, which opinion is correct? So, he thought that maybe there is something one important point why it is happened, because every observer say that different velocity. This is also true for the velocities of Earth, the Sun and the entire Milky Way galaxy. On the other hand, Maxwell found that the speed of an electromagnetic wave such as light is fixed at an x-orbitant 299,792,458 meter per second regardless of who observe it. However, Maxwell's notion seems incompatible with Newton's motion of relative velocity. Newton's laws are truly universal. Why should the speed of light be an exception? This presented Einstein with a daunting dilemma. This conflict between the ideas of Newton and Maxwell can be demonstrated with another of Einstein's brilliant thought experiment. So, today we discuss about consequence of Lorentz transformation time dilation, and along with this we discuss about thought experiment and a simple example also given here. Thank you.